Okay, so it's good to see quite a few people here for being right after a holiday. But hopefully you saw my announcements, and I just wanted to highlight that I've started grading the projects. They look really good, so great work to everyone, and I'm glad that basically the entire class could submit them. What else was I going to say? I've posted the practice final into the files section of Canvas, and I will give you solutions to that and the midterm, but I'll probably not do that until tomorrow or the day after. So sometime mid this week, just so you have a chance to really try them and really think about them without knowing the answer yet, which I encourage you to do. And especially if you haven't looked at them already, you might consider trying to do it in a sort of timed fashion, or at least timing how long it takes on each problem. And I really did design the practice final at the same time I was writing the final. So they're of a similar style, similar difficulty, similar distribution of questions. I will have additional office hours this week. Not today, unfortunately, because of some meetings I have to have with the physics department and some collaborators, but I will have the regular office hours tomorrow, and then probably 1 to 2 office hours on Thursday or Friday, and probably a review session on Friday as well. So just to get you all thinking about what's to come, I'll make an announcement today finalizing those times just so you have them. But there's just been a lot of last minute stuff coming up. And then like you probably saw, I posted the second lecture for chapter 18. I encourage you to watch that in order to do the homework, and the material in that lecture is fair game for the final. So please ask me if you have any questions. You can email me or come to office hours. But the lecture today doesn't build off of that. So if you haven't seen it yet, that's totally fine. Just watch it when you get a chance this week. And we'll start fresh with chapter 19 on ray optics today. Okay. Okay, so we're gonna have to go through this a little bit quickly. If you downloaded the slides, you may have seen there are quite a few, but a lot of them are more conceptual. So we'll try to focus on what you're expected to do with these ideas. But of course, we need to build intuition so we know what the ideas are that we're thinking about here. So to begin, last week in chapter 18, we were talking about the wave model of light, where we were looking at structures that were at least a little bit similar in size to the wavelength of, in this case, light for optics, but we can think about these objects in the context of any type of wave. So in the same way we had single and double slits for light last week, we could do the same with sound. They would just have to be differently sized openings based on the wavelength of sound. Now, if you're dealing with structures larger than about 1 millimeter, so larger than like pencil lead scale, then we want to use another approximation of the behavior of light, which is the ray model. So anything larger than 1 millimeter-ish generally will be the territory of the ray model. There are some exceptions. I'll touch on some of those, but for the most part, that's the sort of clear-cut criterion. And generally, if you're dealing with any sort of wave, sound waves, ocean waves, we can do all of this sort of optical analysis with those waves as well. We just have to scale everything to fit the wavelength of the wave that we're interested in. And similarly, if we're working with non-visible light, so if you wanted to do X-ray optics or infrared optics, microwave optics, these are all important fields of study that have lots of applications in biology and medicine, but that are effectively the same in terms of the toolkit and the analysis, mathematical and otherwise, that we use in order to understand the behavior. So anyways, the ray model basically just says that we can think of light as a bunch of rays, which are just lines with some direction associated with them. And that, for example, when light flows through these arches, that it makes crisp shadows. You see how there's a nice boundary here between the light and the dark region. we know that if diffraction were important, we would see something where there would be like some light and dark spots in sort of rings. But with ray optics, there's a crisp boundary between the light and the dark region when light travels through some opening. And that's just a result of the fact here that the scale of these openings is much, much bigger than the wavelength of light. So even if there maybe is some minuscule diffraction happening, it's just completely unnoticeable relative to the size of these objects. Okay, so I stole a couple of chunks of text from the book, but these are mostly if you desire to like review the slides for your later benefit. But I'll try to touch on some of these points now. So for the ray model, we have a few different ideas. So the most important is that light travels in straight lines and that it travels at a speed of c, so 3 × 10⁸ meters per second in the vacuum or in air, and that it travels slower in other materials based on their index of refraction. The bigger the index of refraction, the slower the light travels in that material. Of course, that's only for translucent or transparent materials, so things that are that allow light to pass through. Similarly, light rays can cross. So this is related to the idea of superposition. With superposition, we say they can cross once they pass through each other. There's no effect to them, but while they're crossing, there is some effect. In the ray model, we don't even think about superposition, really. We just say that light rays can cross. It doesn't do anything. It's not particularly interesting. Now, when you think about light rays in a material, there are basically 4 things that they can do. And in most materials, they do all 4. So in a realistic analysis, in many situations, we would have to think about them each individually. And we'll talk about these ideas today. But so when you're going from one material to another, light can either reflect or refract. So reflection is something we've mentioned a little bit because it's important for standing waves. But light, when it comes to some boundary between 2 materials, some part of the light will generally be reflected and the rest of it will continue going through into the new material. We call that transmission. And with light, we want to note the fact that as it enters a new material, it tends to change angle. Okay, and I'll go way more into detail on that principle later, but that's what's known as refraction. So refraction is the idea that transmitted light rays, as they go from one material to another, tend to change the angle at which they're traveling. And then the other 2 properties we're going to put a pin in and not revisit until the very end of these chapter 19 slides, but they are scattering and absorption. So scattering is when the light rays sort of bounce off little particulates. Those could be molecules of air, they could be little grains of dust, they could be basically anything that's suspended in a translucent material. Alternatively, light can be absorbed. So that's when these light rays are giving some of their energy to the electrical orbitals on atoms. And then when that energy is dissipated by atomic or molecular vibrations, it's just in a random direction and at different wavelengths. So absorption is similar to scattering, but with scattering, we assume that the light wavelength stays the same effectively. And for absorption, that light wavelength tends to be changed so drastically that the type of waves re-emitted aren't even relevant to the problem. So for example, in visible optics, you might have a kind of tinted glass, like imagine sunglasses. So that those sunglasses are absorbing some fraction of sunlight and they're re-emitting it as heat, which for the human eye is completely unimportant at the scale quantity that is occurring in a sunglass lens. And so the process of absorption we can oftentimes think of as just removing light energy from the equation. But in practice, it's always having to be re-emitted some way, typically through infrared, through heat. That's just kind of the scale that molecules vibrate at in most cases. Okay. And then continuing on with the ray model of light, we can think of every point on an object as being an emitter of light rays. Now, this is a really weird idea, and we'll talk a little bit more about it. But classically speaking, like if you go back to Aristotle, he kind of thought that so earlier philosophy than that thought that everything was luminous to a certain extent, and that's why we could see it. Aristotle kind of flipped that on its head and said humans like emit laser beams basically from their eyes, which cause reflection that makes everything effectively an emitter. But in reality, we know that just the sun bounces off stuff, that those rays come to our eyes, so it's not that hard. Or for example, in this classroom, we have these nice overhead lights. So if you look at the wall, every point on the wall looks bright. It looks lit up. So every point on the wall is a source of light rays. And where are those rays coming from? Well, they're reflecting from the lights, basically. So the lights are actually emitting the light waves, and those rays are hitting the wall and bouncing to our eyes. And for every point along the wall, there's some ray from one of these lights that manages to hit it and bounce to us. Of course, they're also bouncing rays in every direction, so we can all see the wall simultaneously. And we'll get into more detail on how those angles look geometrically and what that process entails in a moment. And then the eye, it's important to remember as we go through this, is its own optical instrument. So what we'll see is that in order to form an image, an optical system has to concentrate light down to a single point. Okay. But that the eye, since it actually is an optical instrument itself, can take rays of light that are parallel to each other and focus them into a point. So for example, when we look at the wall, the light rays that are coming into our eye are not focused to a point before they reach us. They're coming in parallel, basically, or very close to it. And then our eye takes those parallel rays and makes them come to a point using our lens. So each eye has a lens in the front of it. And we'll dive way more into depth about how lenses work, but it's just important as we go through all of this to keep in mind that, let's say you're looking at a magnifying glass. You might say, this is a one lens system. I have a magnifying glass. But in reality, that will always be a two lens system because you have a magnifying glass and you have your eye. So both of those are important if we're trying to think about what we visually perceive in some situation. Okay, and then continuing on with the ray model of light. So there's a bit of very basic, very ancient technology that's good to be aware of and that illustrates some of these properties, which is known as a camera obscura, which literally is translated from the phrase dark room. And so the way that you make a camera obscura is first you get a dark room. So that's this box in the diagram. And then you make a small opening. So it can't be too small or you get diffraction. So it's got to be a little bit bigger than a millimeter. But if it's too big, then it doesn't really work well because you have too many rays entering and they kind of all get muddled up. But if you have a fairly small opening, then we can see in the lower half of this that the light bouncing off of the top of this tree, some of those rays manage to make it through this hole and they form an image of the top of the tree on the back wall of this darkened room. Right, so these rays up here manage to form this part of the image on this back wall of the darkened room. And similarly, the light rays bouncing off the bottom of the tree. So basically thinking of the bottom of the tree as a source of these rays, they just travel in straight lines. They go through this hole and they form an image on the top of this darkened room's wall. And the net effect is that you actually get an inverted, but to scale image of whatever's outside of the room. And if you just put some mirrors in the system, you can make it right side up. We can talk about how to do that later. And so this was an ancient technique used by artists that people still use today to paint very accurate landscapes because you can basically just trace them by projecting them onto a wall or a canvas like this from the outside. And we can see that there's some really nice geometry here. So we have one triangle. Let me erase these blue dots really quickly. So we have one triangle here. These aren't right triangles. They are isosceles triangles. I have another one right here. And these two triangles, the blue and the green, are similar. So they have the same angles, but they are scaled from one another. And so what we can say is that the ratio h naught over d naught, this tells us basically how big this blue triangle is. Or sorry, I already messed this up a little bit. So the ratio h naught over hi, or as the book says, hi over h naught, this is telling us how small is this image relative to this real object. So the ratio of the heights is the same as the ratio of the distances. So the distance of the tree from the opening and the distance, the length of the dark room. So di over do. This is just a fact of geometry. And as we'll see as we go through this chapter, you're going to have to revisit some geometrical principles, which isn't always the most fun, but we'll try to make them as painless as possible. And in a lot of situations, you'll have an equation which is the thin-Lenz equation, which will make the analysis a lot easier than it would otherwise be. But in this problem, we just have to go from the fact that we have similar triangles, and we can see that if we have a fairly small room compared to the actual distances, then we'll have a shrunken image. So this little tree here is much smaller than its real life counterpart. And that's a result of the fact that this room is much smaller than the distance outside. We could do it the other way around. If we had a very big dark room, we could even make things life-size if we had a big enough dark room. But in most cases, your room will be smaller than the outside. Okay, so just to check your understanding here. So if we have this horizontal light that's illuminating a vertical opening, and if this opening, it doesn't say it in the problem, but let's imagine that this opening is bigger than a millimeter. So it's like, a reasonably sized opening. And we let the light pass through it and land on this screen. So the screen is just like this projector screen here. So then which pattern do we see in this situation? Anyone want to hazard a guess? Who thinks we see A? Okay, couple. Who thinks we see B? Couple. C. Nobody likes C and D. Okay, so we would see D if this were a very small opening. So that was the focus of that second chapter 18 lecture. So if you recognize what that is, then you probably watched it. But for a larger opening, we would see A. So we just imagine, even though the light is oriented horizontally, every point from that light, we can imagine emanating out in rays, straight lines, and some of them will pass through this vertical opening and cast a vertical shadow or a vertical bright spot onto this screen. So it doesn't matter how the light is oriented, it just matters how it's allowed to travel. In this case, it's constrained by the opening. Okay, so that was section 19.1, all about what it means to be thinking about the ray model. But now we can move on to reflection, which the theory of reflection is one of the simplest physical theories that we have. But of course, when we actually want to do problems with it, they can start to get tricky because of geometry. So the theory of reflection is just that whatever angle light is shining on a surface with, we call that the incident angle, or the angle of incidence, will be equal to the angle that it reflects off with. So if we have a flat surface, this is very straightforward, and we can see it happening in this lower diagram, that light shines in with some angle, and it shines out with that same angle. And in optics, we typically measure angles relative to what's known as the normal. So we can see this line drawn. So the normal is just a line drawn perpendicular to the surface. And the reason that we care about the normal line is just goes to like some concepts from Calc 3, so vector calculus. It's just part of our toolkit for how we define a surface. And so it kind of trickles down even to the level of reflection, physicists just love to talk about angles with respect to the normal. So you can see here that the angle of incidence is measured from this perpendicular line to the ray of light that's coming into the surface. That's theta sub I. And similarly, the angle of reflection is measured from the normal to this ray being reflected out from the surface. And we don't really think about the plus or minus signs of these angles. We just say that the theta here, you know, it's greater than or equal to 0, and it's less than or equal to 90 degrees. Well, really, I should say strictly less than 90 degrees. Although so it can be 0. You can have light that shines just directly and bounces directly off. But if you try to have light that shines at 90 degrees, that would have to travel through the surface. So that would not be reflection. And we'll talk about what that actually is pretty soon. It has a nice relevance to a lot of situations. But we can also say that when light reflects, it reflects in some plane that's perpendicular to the surface. Okay, so here we're shining light on this mirror, and you can see we're shining it in the direction of sort of the width of this glass, and it reflects back out on that same plane. So usually that'll be obvious, but it's just good to tell you this so that it's, you know, somewhere in your mind, somewhere in your notes, that if you're doing some geometry problem with reflection, that it's all happening in one plane. So you can always draw a flat surface that will contain both the incident rays and the reflected rays. Now, this is what reflection looks like on a flat, nice mirrored surface. We call this specular reflection, if you're trying to be specific. So anything that you would normally think about when you think about reflection, namely mirrors, those are an example of specular reflection. Of course, we can have situations, so you can imagine what if you had something like a disco ball that was still made of mirrors, so still reflected very well, but all those surfaces are at different angles to each other. So how do we think about light coming, if light hits a disco ball, how do we think about it being reflected? And the answer is we have to do this theta I equals theta R for each surface. So a disco ball, right, has a bunch of surfaces. It's some complex shape. But we can look at each one and think about how the light hitting it has to bounce out and that these two angles are equal. Okay. But similarly, you know, we might have some ray hitting here and it bounces out like this and has a different theta I and theta R. So each surface will have, each flat surface will have a unique instance of this law of reflection. Okay. And if we have a curved surface, we have to start using calculus, right? We have to start thinking about how any curved surface is just some infinite number of flat surfaces all next to each other. Of course, we won't cover that in this class. Okay, but instead of specular reflection, we can also have diffuse reflection, which is basically reflection from anything not particularly mirror-like. So for example, the wall here, again, is not a mirror. I can't see my image in it. But the light that hits it has to get to my eyes somehow. And so that process is an example of reflection. The fact that I can see the wall means that light is reflecting off the wall into my eyes, but it's not doing so in a really, really nice way that allows me to like see my image in the wall, and, you know, it's not shiny. So that's an example of diffuse reflection. So there's a microscopically rough surface. Even very smooth objects might have microscopic indentations that sort of cause the light to seem to reflect in a bunch of random directions. Of course, they're not random if we draw perpendicular surfaces at each little chunk of this complex, you know, scratched up surface. We would see that the law of reflection holds for each of those. But if you have some complexly cratered, you know, roughed up material, we can't really predict how the light will reflect off of it. So we just think of the fact that if we have some arbitrarily rough surface and we shine light onto it, we can kind of just imagine that light traveling off in every direction. And in fact, that's very similar to this point about the ray model, that we imagine each point on a illuminated object as being an emitter of rays that are traveling outward in every direction. So that's a result of diffuse reflection. Okay. Any questions so far? Good. So we'll try out a problem. And this problem expects you to be able to draw this picture, I think, but I wanted to include it because my picture drawing is really terrible. And that'll kind of be the trend for problems in this chapter, is that I tend to include a lot of pictures. But many times you'll be expected to draw these pictures at least roughly yourself. And I'll walk you through how to do that in as many situations as I can. But it's important to understand that you'll be oftentimes expected to draw figures based on some textual description. Okay, so in this situation though, we have a full-length mirror on a closet door that's 2 meters tall. So this right here is the mirror, and you can see that it's denoted 2 meters tall. The bottom touches the floor, so we draw that here. A bare light bulb hangs 1 meter from the closet door. So the light bulb over here is 1 meter from the door and 0.5 meter above the top of the mirror. So you can see the actual ceiling might be taller, but that doesn't matter here. So we can just draw the bulb as being sort of at the ceiling height. So you can see they did give us enough information to draw this figure. And they now ask, how long is the streak of reflected light across the floor? So you can imagine if we did this in a dark room, we had a mirror on one wall and a light bulb shining on it, that on the floor, there would be some bright spot lit up by the reflected light from the mirror. But if we got far enough away, it would be dark. So we can intuitively expect there to be some sort of bright spot like this near to the mirror. And you can see that what they do here in order to start to analyze this problem is to draw rays. Okay, so we can think about this light source, this light bulb, as emanating rays in every direction. But only some of those rays will be interesting to us. So for example, we can imagine what happens to the ray that hits the bottom of the mirror, or very close to the bottom, and it's just going to be reflected in such a way that it illuminates this region right next to the mirror on the floor. So very close to the mirror. And then we can kind of imagine what would happen if we had some ray from that had a different initial angle. We could see that it would follow the law of reflection. So it would roughly come out in the middle somewhere. So any of the rays that hit the middle of the mirror are going to come out somewhere in the middle of this bright region. But since all that we care about is the total length of this bright region, this reflected streak on the floor, we can think about what would be the ray that goes the farthest. And that's just the one that hits the top. So whatever ray hits the top of the mirror, by geometry alone, that will be the one that goes the farthest. And so you can kind of test this out like we just did here by looking at a couple of different rays and come to the conclusion that the ray from the top will be the one that goes the farthest. And so then we have to start thinking about our geometry. So we have, if we think about, I'm going to erase this actually so that we can communicate more easily here. So if we think about, there's a vertical line here and there's a vertical line here, and this part of the ray acts as a transversal. And so we get that these two angles are equal just from the fact that we have, they're like opposite interior angles or something like that. So some transversal property of lines. We can also think that there are two right triangles, and so we have this angle here and this angle here, which are also equal to one another. And so if we draw these two right triangles, they would be similar, and they would have angles that add up to 90 degrees in the corners. So that's another way of imagining this. And conveniently enough, this angle theta right here is actually the angle of incidence. So this angle right here is our theta sub I, because it's an angle measured from the horizontal. And since the mirror is vertically oriented, a horizontal line is the normal line. So if we're measuring the angle from the normal line, that would be this theta I right here. And so reflection tells us that this angle, which is theta R, is equal to theta I. Okay, so that's where we actually use the law of reflection. And then yet again, let me try to draw this in a different color. We have this horizontal line, which is of course parallel to the floor. And so this theta R here is the same as this theta here. And that's a consequence of that sort of opposite interior angle principle, or alternatively, we can say that both of those corners add to 90 and they have the same complementary angle. Okay, so then in essence, what we have is a right triangle with angle theta at the bottom, 90-degree angle here, and a height of 2 meters on this side, and we want to find the length. So once we get this theta, that's a totally well-defined problem. We can just say that tan theta is 2 over L, and so L is 2 over tan theta. And now to get theta, we just have to look at where we first saw it. And we first defined it just in relation to this top triangle. You can see that up here, this was theta, this was 90, this was a length 1, and this was a length 1/2. So in order to get theta, all that we have to do is take the inverse tangent of 1/2 over 1, which is just the inverse tangent of 1/2. Okay, and if I pull this up, so plugging this into our calculator, we get 26.6 degrees. And then plugging that angle in for theta down here, we find an L of 4 meters. So that would be our final answer. So you can see that problems concerning reflection are really just like a throwback to geometry. We have to carefully define some angle. So in this case, we just define this angle theta in relation to the uppermost triangle. And then we kind of follow that angle through the problem using different theorems to make sure that we find either equal angles or related angles, right? We can use the fact that the angles in a triangle add up to 180 degrees. We can use these sort of transversal theorems from geometry, complementary and supplementary angles. And then at some point along the way, we'll use the fact that the angle of incidence equals the angle of reflection for any light that's reflecting off of a flat surface. And so that'll allow us to get some final piece of the picture, and we can then put it all together and find what we're looking for. Okay, so you'll get some practice with this in the homework if you haven't already, but this is a great time to mention this TikTok that one of my cousins sent me, which was, can anyone explain how the mirror knows the object is there, even though there's this piece of paper in the way? And so hopefully by now this is pretty reasonably answerable, but just to help you out, we have a couple of diagrams. So you can see that if we have some object in green, which it could be a light bulb that actually is emitting light, or it could just be anything where light is diffusely reflecting off of it. So it's effectively a source of light rays. Then those rays can hit a mirror, and depending on the angle they hit with, they'll bounce off with the same angle. So different rays will go in different directions. It's just a matter of how they hit the mirror originally. But you can see that if we have some object in the way, some piece of paper or something, that doesn't interfere with the rays that are going at these wider angles, right? So they'll just easily bounce off and, at some angle, and then whatever angle they bounce off with will be the same as their angle of incidence. And that if we follow a few of these rays, as we do here, that they'll bounce off and be close to parallel once they leave the surface of the mirror. And our eye then interprets those, it concentrates that light down to a point and interprets it as an object being on the other side of the mirror, right? So this is what we call a virtual image. We'll see plenty more examples of virtual images in chapter 19, the idea with a virtual image is that the optical system is somehow creating light rays that are spreading out. So that's the essence of a virtual image. And the reason we call that spreading out of light rays an image is because our eye is a lens. And so it'll see those spreading out light rays and be like, okay, they're coming from something. And that something couldn't be an optical system because that wasn't around when the eye was evolving. And so it just interprets that as an object farther away generally, where the light rays seem to be emanating from. So you can see here that if we follow these light rays back, they seem to be emanating from this point P prime. And so we call that the location of the virtual image. So in this example, you can see that the light rays, what they're doing is they're hitting the mirror and they're bouncing towards our eye. They're spreading out as they do so, but that our eye sees those light rays and thinks that they're emanating from some point P prime, which is seemingly located inside of the mirror, right? And so it doesn't matter that there's this piece of paper in the way. The light rays are bouncing at a wide enough angle that they don't hit it. It just matters that the mirror is large enough and that we're sort of sideways enough that we can see those rays and that our eyes can reconstruct them as a virtual image. Okay, and so putting that all together, we can see here that if we have this point P prime at the top of the actual little pine tree, that a bunch of light rays are emanated from that, diffusely reflected, and then hit a mirror and end up diverging, so spreading apart after they hit the surface of the mirror, simply due to the law of reflection. And our eye interprets those as if they were coming from this point P prime within the mirror. And conveniently, whatever distance away this object is from the mirror, we interpret that as being an equal distance within the mirror. So if your hand is 2 meters away from a mirror, it'll look as if it's 2 meters behind the mirror. This is just something that you can derive from the geometry of the system, basically from this idea of similar triangles. And that similarly, light from the bottom of the tree will bounce off the mirror and seem to be emanating from a point Q prime. And so importantly, mirrors don't invert things vertically. So if you look at your image in a mirror, you know, the top of your head is up and the bottom of your head is down. Of course, they do invert things horizontally, or they appear to. So, you know, the light from your left does come back to your left, the light from your right comes back to your right. But when we look at that light, we interpret it, since we can only see the front of an object and only the front is reflected back to us, we interpret that virtual image as if it's mirrored. You know, we even use the word mirrored to describe this, meaning that the right and the left side are sort of transposed. So that's not a property of the light, that's a property of our, you know, brain's interpretation of what's being reflected. Okay, so before we move on, any questions about reflection? That's where we're going to leave it for quite a while until we get into mirrors that are curved, which will be later in the chapter. Okay, so the next principle that we need to examine is refraction. So remember, this is something that happens when light travels from one material to another. Okay, and in chapter 17, we talked about this a little bit, and in chapter 18, when we were looking at thin films, for example, we had to imagine that some of the light that was going through this thin film was being reflected and some of it was being transmitted. And so we call that light that's transmitted refracted light. So transmission is the same thing as refraction. It's just that this is meant to emphasize that the angles change. Okay, and so we can see an example where we get both reflection and refraction in this image. So every time, in this image, there's air surrounding a glass prism, which is just a chunk of glass. There's nothing particularly special about it, other than the fact that it's very clear and polished and, you know, hopefully free of dust and fingerprints and such. And so initially we have some light ray shining on this prism, and some fraction of that light will be reflected. And for that light, we can just draw the normal line, and we can say that the incident angle equals the reflected angle and be done with it. Of course, we might have to, that might be hard to find that angle just because of the geometry of the system. We would have to know how this triangle of glass, what its angles are, but it's not anything that we haven't seen before. However, what is new is that we have this light that is transmitted, that passes into the glass. And what I want to highlight is that so this is the normal line. Sorry, let me try to draw this one more time. So this is the normal line, and that the angle that this light is coming in with is not the same as the angle that it's traveling through with. So the light bends right at that moment when it passes from the air to the glass. And that's what it means for light to refract. So refraction is the bending of light as it travels from one material to a second material. And the way that it bends depends on those two materials and what order they're in. And so we'll write down how that works in a moment. That's Snell's law. You may have seen it before. But I wanted to highlight one case where we see this, which is if you just put a pencil or a straw in a cup of water, that it'll appear to be broken. It doesn't look quite right. And that brokenness is a result of the light coming from the pencil. So every point along this pencil, since it's illuminated, is acting as a region where diffuse reflection is occurring. So every point on the pencil is effectively a source of light rays. It's just that the light rays in the air bounce off the pencil and travel directly to your eye and don't change material. So those have no refraction, just reflection. However, the light waves that are emanating from the part of the pencil under the water, those light rays have to first pass through water and then pass through air in order to get to your eyes. And when they transition, when they go from water to air, they change angle. And that changing of angle is what causes, you can see there are two things observable in this picture. One thing is that the pencil is broken, and the other is that the pencil looks bigger, looks thicker under the water. So that's not an accident. That's another principle of refraction. And we'll talk about why both of those things occur just in a moment. But before we move on, I just want to also mention that at the second surface, where we go from glass to air, we again get refraction. And you can see that this angle and this angle, that these are not the same. And it's not visible, but we also would get some reflection off of this surface that would go back into the glass. Generally, that secondary reflection is very minimal because whatever light manages to make it through and be transmitted in the first instance will only be a small fraction. And so the internally reflected light will just be a fraction of that fraction. But there are some cases where that internal reflection is important, such as fiber optic cables and in the making of rainbows. And we'll talk about both of those in the slides in a little bit. Okay, so I couldn't find a good diagram of this. This is from like some old PBS video, but I just remember this, some sort of image like this in my head from when I was a kid. So I had to find it for you. But anyways, if we want to think about how refraction works intuitively, what we should think about is what this lifeguard would do in order to save this drowning person. So naively, you might say that the lifeguard would travel in a straight line to the person, because that, typically we think of straight lines as the most efficient paths that we could travel, right? If I wanted to run to one of you, I might travel in a straight line towards you. That would tend to be quicker than taking some roundabout path. However, we have to be realistic and say, well, a lifeguard can, even though they're maybe good swimmers, they can probably run on land faster than they can swim through water. So if you actually want to get to this person really quickly, what you would want to do is you would want to take a longer path in the sand and a shorter path in the water. Now, the most extreme version of that is that you could go all the way in the sand and then go directly in the water. But intuitively, we can imagine that probably isn't the fastest way either, because we had to travel, this extra distance on the land in order to go perpendicularly. So it turns out that the fastest path is something like this green path here. And in fact, this is very, very similar to what light does when it refracts. I guess you could probably figure that by the fact that I'm telling you, but what we can do is we can draw the normal line in this picture, and we could call this, let's say, θ1, and this θ2. And you can see that if we're thinking of the lifeguard, the material that they can travel through more easily, that they can travel through faster, will have a larger angle than the material that they can travel through more slowly. So θ1 is greater than θ2, and the speed in material 1 is greater than the speed in material 2. Okay, and this is the foundation of Snell's law. So this is the foundation of the law of refraction. And it turns out that this statement that I'm trying to make, this analogy, that light would want to do something similar to the lifeguard, that light would want to take the fastest path that it can, where it takes into account the fact that it can move faster in some material than in another. So it should travel more in the material that it can go fast in and less in the material that it can move slowly in. This has a name in physics. It's actually known as Fermat's principle. And we can actually use Fermat's principle to derive Snell's law. That's not how it was done historically, but it's how we now think of it in modern physics. And actually, this principle is the basis of almost all of modern physics that I really wish I could tell you more about. So the science of quantum field theory, where we can study the most detailed aspects of fundamental particles, so sort of what we do at particle accelerators and such, is all a starting place for it is Fermat's principle. Fermat's principle is one of the first really, really powerful ideas in physics that just changed the way that we view the principles behind the laws of nature. So thinking about the fact that the simple idea that light wants to minimize the time it takes to travel from point A to point B, taking into account that it can travel faster in some materials than others. So getting away from that deeper angle here, and going back to what we care about, the speed that light can travel through the different materials is based on the index of refraction, right? So the speed that light travels in some material is the speed in the vacuum, which is 3 times 10 to the 8th meters per second, divided by some number n for that material. And those n's are these indices of refraction. So for the vacuum and for air, we take n to basically be 1, which is a very good approximation. And then for other materials, we have to find it empirically, or we can use some advanced quantum mechanics stuff to calculate it. But for the scope of this course, you'll always just be given, or either given directly or given all of the things needed to calculate the index of refraction in a problem. And so we see some examples. The most critical one to know is that water is 1.33. Again, you don't have to memorize any of these, but it's nice to have a couple in your mind when you're doing these problems, just so you know what's a reasonable value. Anything bigger than 2 is pretty unusual. So you can see yet again, diamond is kind of weird because it has a very strong set of intermolecular bonds, a very regular crystal structure, which causes light to travel quite slowly through it. And so that's one way that you can test if a diamond is real. You can see that cubic zirconia, which is a common sort of fake diamond, is noticeably smaller in index of refraction than the real thing. So then looking more closely at how this refraction can be drawn in terms of ray diagrams, on the left, we're going from a low index material to a high index. So here the light is moving fast, and here it's moving slow. Whereas on this side, we're doing the opposite. It's still slow and fast, but you can see that we're going the opposite way. So remember, fast means small n. slow means big in. So the bigger the index of refraction, the slower the light is in that material. And what we can see is it's exactly like the case of the lifeguard. So light travels for a longer path, so at a larger angle in the material that it's fast in. And then it bends so that it travels a shorter path, so a smaller angle in the material that it's slow in. So somehow, and in order to understand how, you really have to get into quantum mechanics. Light feels out all the possible paths it could take, and then takes the one that's fastest. It's really quite magical that this works out. And we can nicely describe the way that this happens with Snell's law. So we know that the faster material, that the light is at a bigger angle in it. But in order to actually calculate the angle, we have to take into account the exact functional form that this comes in. And it turns out that it's through the sine function, so sine theta. And like I said, there are some really nice derivations of this coming from Fermat's principle. I might post a video to one if you're interested, but it's not necessary to know how this comes about, only to know that it exists and that intuitively what happens, that the light takes more time in the faster material. And so what we can see, remember that sine theta, it's very similar to theta for small angles. So that won't be true for most of Snell's law, but we can use it to build some intuition quickly. So we can say that when n is big, so let's say that n1 is 2, and let's say that n1 is 1. So in order for this to work, that means that theta 1 has to be small, and theta 2 would have to be big. And you can see that that would be, let's make this match the picture here so that we can build some intuition. So in this picture, they assume that n1 is smaller than n2. So let's say that n1 is 1 and n2 is 2. Then if we plug that into the formula, then in order for these two sides to be equal, theta 1 has to be big and theta 2 has to be small. And that's in fact what we see. Theta 1 is the bigger angle, theta 2 is the smaller angle. And if we want to know exactly how much bigger or smaller, we have to actually plug into the equation. And so let's do that. And this is a nice problem, I think, because it makes you do some geometry. So in this example, we have a laser beam that's being deflected by a prism, so a chunk of glass. And that chunk of glass is cut in such a way that it's a 30, 60, 90 triangle. And actually, I realized that we're a little bit over halfway. So before we dive into this, let's take a 5-minute break or so to reset, and then we can do the problem together.
So you said that M here can be but if I click this number,
Yes. So that would, the way that happens is if the theta is 0, And so that's just telling you that there's a bright spot horizontally
Is there a
across.
horizontal? So I guess what's the wording that we would use when it's like ends with 0?
I would call that the central maximum,
Okay.
and I would call 1 like in physics, we call it the first order maximum, and then 2 is the second order,
Okay.
and so on. So the higher end would be in order.
Okay, all right.
Yeah, good question, good question. That was for the double slit or for the diffraction grading? One of those two?
Yeah.
Okay, good, good. Okay, so we should get back into the slides, unfortunately, but hopefully the break was a little helpful. So for this problem, it's a pretty straightforward application of Snell's law, but it's also a good example of how to actually find the angles that you need, you know, in the context of a prism, where we typically prisms are triangles, so we will want to use some idea about the geometry of a triangle. And what I want to highlight is that the angles θ1 and θ2 in Snell's law are measured relative to the normal. So if we want to use the sine function, we have to measure these relative to the normal. If you look at some old textbooks before everyone sort of settled on this form of Snell's law, sometimes they would measure them from the surface and would use cosine. But in this class, I would encourage you to just stick to what we have, stick to what's in the book, and use sine and use the angles relative to the normal. So to find, so if we imagine looking at this top ray of light that we see as refracted, that we need to find the angle relative to the normal, which is, we can draw the normal visually. It's going to be at a 90-degree angle. And this one angle here would be θ1. And then this angle here would be theta 2. Okay. And so how do we find theta 1? That's the issue. And in order to find it, what we have to do is we have to think about the fact that when we cut horizontally across this triangle, we get a similar triangle on the top. So this is also a 30, 60, 90 triangle. And then between, let me try to draw this in, between this surface and this surface, we also have a 90-degree angle, right? Between the black line and the red line on the hypotenuse, we have a 90-degree angle. So from that, theta 1 is complementary to the base angle, that 60 degrees. So theta 1 is 30 degrees. And then theta 1 and this top part of theta 2 are vertical angles, so they're opposite. So those two are equal. But theta 2 is that upper part plus this 22.6 degrees. So theta 2 at the end of the day is 52.6 degrees. And now we can actually use Snell's law. So here the Snell's law question is, what is the prism's index of refraction? So what we're interested in is N1, right? You can see that for the surface that we've found theta 1 and theta 2 with respect to, we're going from the glass to the air. So for the air, N2, that would just be 1. So we can write N1 sine 30 degrees equals 1, which is N2, times sine of 52.6 degrees. And now we can just solve for N1 by dividing by sine 30 degrees and get 1.59, which is a reasonable value, right? It's between 1 and 2. That's kind of the way you can typically check if an index of refraction is reasonable. So for glass, you can see back here, the book lists typical glass as 1.5. And in reality, that can range quite a bit. There are lots of kinds of glass out there in the world. Everything from sort of pure silica dioxide, like window glass, to borosilicate glass that labware would be made out of, to optical glass that might have some other purposefully included impurities. So this is what I would say is a very reasonable value. Are there any questions about how I got the angles here in order to actually solve this problem, right? That's often the hardest part for both reflection and refraction, is just getting the angles relative to the normal so that you can actually solve using the equations that we're using in this class. Yes. So this black line is the normal. So this line right here is the normal. And you can see that because it's perpendicular to that surface, the outer surface where we have refraction occurring. You might say, okay, Cannon, why didn't you just use this first surface, right? This inner surface. And that's because for that inner surface, the angle is 0. So theta 1 is 0. And you can see that if we have N1 sine theta 1 equals N2 sine theta 2, that if this is 0, then that causes theta 2 to also be 0. So importantly, just from looking at Snell's law, we can say that light that goes perpendicularly through a surface will just not be bent. Because if you're shining light perpendicularly through a surface, the light doesn't really have an option to bend. You can only bend light, you can only change the component that's parallel to the surface. That's actually where the sine theta term comes from, is it's sort of grabbing the parallel component and scaling it by the ratio of the indices of refraction. Okay. Any other questions about this? I think this is a good illustrative example of how to work with Snell's law. Good, good. So like I said, sometimes with refraction, so typically with refraction, we're thinking about transmitted light, but sometimes refraction can get so strong that it actually becomes reflection instead. So the beams of light, so you can see this beam of light is almost at an angle of 0. So it's barely bent at all. It's just transmitted from the water to the air. The light here is bent, right? This is just using Snell's law. So that's refracted. Here it's bent and refracted, but this beam actually is reflected, not refracted. So what we can see from this set of images is that if we make the angle large enough, so if θ1 is big enough that refraction will actually become reflection. So notably for this last ray, for this blue ray here, if I can draw, there is not refraction happening. So this light is not refracting, it's just reflecting. Theta I equals theta R here. And so what's happening? Well, we can ask ourselves, thinking about Snell's law, N1 sine θ1 equals N2 sine θ2, we can ask ourselves, what happens if this ratio gets so big that it causes one of the angles to be 90 degrees? Okay. So when sine is 90 degrees, when theta is 90 degrees, the sine would be 1. So we can ask ourselves, what happens if sine θ1 equals N2 over N1? And we call this angle θ1 the critical angle. So that's what this formula over here is solving for. And that's the angle that for that angle or bigger, we achieve reflection instead of refraction. And the reason is that you can see in this right image, when the light travels at a 0 degree angle, it just goes straight through. When it travels at a slightly bigger angle, let's say 10 degrees, it's bent a little bit. When it travels at a bigger angle, let's say 30 degrees, it's bent quite a bit. But eventually it's bent so much that it's actually bent 90 degrees. So this angle where it's bent 90 degrees by refraction, we call that the critical angle. But light can't actually be bent 90 degrees by refraction, because if it were to be, it would travel right along the edge of the surface, which would be really bad in relation to Fermat's principle. And so what actually happens is the light gets reflected off the surface, that inner surface, and just stays inside the first material. So it doesn't actually get transmitted at all. The entirety of the light is reflected within the material, and none of it is transmitted. And so we can see that in this picture on the left, that really, truly, all of the light is transmitted, all of the light is reflected, none of it is transmitted in that rightmost picture. Now, I want to highlight that in these other pictures, you can see in this one, a little bit of the light is reflected. So whenever there's refraction occurring, there's always a little bit of reflection as well. That was important in that first image of the prism we saw, where there were both reflected beams and refracted beams. But whenever the angle is greater than 90 degrees, in the case of refraction, we get all of the light reflected within the material. And so we call this total internal reflection. Or in the book, they will just say TIR all over the place, which I was very confused by at first. So TIR is this idea that if you refract light at a large enough angle, and importantly, that you're going from a larger index of refraction to a smaller index of refraction. So you have to be going from a large N to a small n. If you try to go the other way around, you don't see this behavior, because the light would actually, bend more and more inward in that case. So when going from a large end to a small end, so for the example here, from water to air, if shining the light at a large enough angle, we'll achieve total internal reflection. All of the light, instead of refracting, will just bounce off that surface. Which is really a weird phenomenon because we tend to not think of the surface like between water and air as a particularly good mirror. But for large enough angles, it's pretty much a perfect mirror. It reflects all of the light. And so one really important use of this is in fiber optic cables, which are the basis of these sort of scopic style surgeries. And the idea behind them is that we take some tube of glass, some cylinder of glass, and we have an inner part that's a high index. So this part has a large in, and it has a cladding, so another layer of glass that has a smaller index. And so as long as we shine the light at a big enough angle, right, you can see that we have to measure the angle relative to the normal. So that means as long as we shine the light down the tube, which is, what we would want to do anyway, is we shine the light down the tube, then the light will totally internally reflect. That's this TIR. So as long as those angles like θ1 here are greater than the critical angle, so as long as we're shining it pretty straight down the tube, then the light will just bounce along this little pipe of glass and be undisturbed. And so we can use this to actually look inside of people. If we, have a little flashlight, on the outside of this tube. So if we have a long tube and we have a little flashlight on the edge of it, then whatever light bounces off the person's tissue will enter this tube and come out the other side after having bounced down the tube, undergoing total internal reflection along the way. And that this is really nice. It's much better than trying to put a mirror, because making mirrors is hard, whereas making tubes of glass still kind of hard, but much less so, much less tricky manufacturing wise, and also just more reliable. They can't get scratched or dinged up in the same way that the surface of a mirror can. All that we need is these two layers, one inner layer with a large index of refraction and an outer layer with a smaller index of refraction. And we get this nice sort of fiber optic cable quality that you can see here. So it's useful in surgery. It's also useful in internet, right? If you have Google Fiber or something at your apartment, then you would know, you would see the benefits of transmitting data via this sort of mechanism. So we can just use flashes of light traveling down a tube like this to contain some file that you might want to get from the internet. Okay, so we have an example problem here with what you would see looking down into the water, basically. So in this problem, a woman lies on a paddleboard, floating on the still surface of a tropical lagoon, scanning the water below, and a sea star rests on the sandy bottom of the lagoon 3 meters below the surface. What is the diameter of the circle on the surface of the water inside which the woman can see the sea star? So what's happening here is, there's diffuse reflection off the bottom of the ocean. And so some of those rays are bouncing off this green dot, which is this little sea star. And those rays are bouncing off the green dot and traveling outward. And in order for the woman to see the sea star, the waves or the rays of light have to go from the green dot out into the air, right? They have to actually be transmitted from the water to the air, which means they have to be refracted. So if the woman is too far away, then those rays that would be going towards her, if there weren't a change in material, instead they undergo total internal reflection, because this angle, this theta here, is bigger than the critical angle. So we achieve total internal reflection for far enough distances. So you can try this yourself. If you go over to the arc pool and you throw something in the bottom, you can only see it if you're close enough to it. If you go far enough away, then whatever light is emanating from it due to diffuse reflection will just be contained within the water by total internal reflection. This is why it's really hard to find stuff at the bottom of a pool. You have to be reasonably close. If it's a big pool, you'll notice this effect. And so how do we find that? Well, we have to just find where does this critical angle occur, and that will define sort of the boundary of this circular region. 1 second here. Okay, and so to find the critical angle, we just go back a couple slides. It's just the inverse sine of n2 over n1. So this is the inverse sine of n2, which is 1, right? The air, the light rays are going from the water to the air over n1, which is 1.33. And so just by taking this inverse sine, we get 48.8 degrees. And now that's this angle down here. I'm gonna erase some of this extra stuff. So this is theta c. And so now what we can do is we can draw a triangle. We can say that this is our theta c, this is 90 degrees. And we want to know what d is. So this would be d over 2, right? We want to know the diameter. This bottom leg of this right triangle would be the radius, if you can see that. And we know that the height of this triangle is 3 meters. So this is just a well-defined trig problem. We could just say that the tangent of theta c equals d over 2, over 3. So d over 6. So d is just 6 times tan of theta c. And plugging in, I get 6.9 meters. So you can see it's a pretty big distance within which we can see this C star. So within, if we interpret this as a radius instead, that would be around 3.5. So within 13, 14 feet, we could see this object, but if we got farther away, we wouldn't be able to see it anymore because the light emanating from it would be totally internally reflected. Okay, so continuing on with refraction, like I mentioned earlier with the pencil in a cup of water, we see that things that are underwater or in a more or in a material with a higher index of refraction seem to be enlarged. And so the reason for this is that when the rays travel from the slow material to the fast material, so from the water to the air, they spread out. They end up going at a larger angle. So this angle here is larger than this small angle in the material. So theta 2 here is larger than theta 1. And our eye interprets this as the object being closer than it actually is. So here the green rectangle is the actual ruler, but our eye sees this spreading out light and traces it back to where those rays seem to have all coincided. And we call that this point P prime. And that's where our eye imagines that the image is, or imagines that the object is located. And so this is an example of a virtual image, right? The ruler isn't really being projected onto that point. There's no real light originating from that point, but our eye, as an optical instrument itself, interprets this spreading out light as if there were some object at this point P prime. And so that's why we see the ruler enlarged. And we can go through the geometry here, which the book does in great detail. And I don't think I will in much detail, other than to say that, again, we have similar triangles. So we just follow this idea of similar triangles and say that the ratio of S prime and S is related to the ratio of N1 and N2. And by putting that together, we get a way of figuring out how much closer it appears that the ruler is, which is S prime. And it's just this ratio of N2 over N1. Okay. And so again, we can do an example, and this will probably be what the last thing we can fit in class today, of a person looking down at their feet under the water. And if you do this, then what you'll see is that your feet appear a little bit bigger. So it looks like they're closer. And so what we can do is we can go back to this equation that S prime is negative N2 over N1 times S. And we can look at what they give us here. So normally when she tips her head forward to look at her feet are 1.6 meters. So S is 1.6 meters. How far away do her feet appear? So we want S prime when they're under 0.6 meters of water. Or sorry. This total distance is S, or sorry, is D plus S. So D plus S is 1.6. Our S is this 0.6 here. Okay, so to solve this, it's just a pretty straightforward plug and chug sort of problem. Our N2 is air, so that's 1. Our N1 is water, that's 1.33. And our S is 0.6. So for S prime, we get negative 0.45 meters. And the negative here isn't actually telling us anything about the physical distance. I should have mentioned that before. The negative here is just telling us that this is a virtual image. So we'll see this in more detail as we go through the rest of the chapter, but having a negative sign isn't anything about the physical geometry. It's just telling us what kind of image we're seeing. So this actual distance S prime is just 0.45 meters. And so if we put this together, we could call this D prime, which is the total distance, is this D plus S prime, where D we can solve for up here is just 1 meter, 1.6 minus 0.6. And so in the end, the feet appear to be, so this distance here, 1.45 meters. D is 1, S is 0.6. Okay, so that's all we have time for today. Like I said, I unfortunately can't have office hours today, but I will have some tomorrow and Thursday, and probably a review session on Friday. So if you want, you can see me quite a bit this week, but I'll leave it there for now.